Friends, welcome to the tutorial series on network analysis made simple. This is a module-wise ELE Electric Circuit Analysis paper solution series. In this tutorial, we are going to solve VTU CBCS scheme electrical circuit analysis questions of module 1 of June-July 2017 paper of syllabus 15E32. I prefer to emphasize on basic concepts, strategy and thinking process rather than detailed mathematical steps. I am sure you are well equipped with required mathematical skills. Hope you will enjoy the travel. Let's go ahead. Friends, first let us solve the question on source transformation. In this question, we are required to obtain a single voltage source network across the terminals AB of a given network. Observe the given network. There are two practical current sources, one of 10 amperes in parallel with 2 ohm and the other of 5 amperes in parallel with 4 ohm. Also, there are three practical voltage sources, one of 5 volts in series with 2 ohm, another of 10 volts in series with 2 ohm and the other of 20 volts in series with 4 ohm. The strategy will be to go on converting the sources one by one and go on reducing the network till we reach a single voltage source network. So, by converting 10 ampere current source, we get a voltage source of 10 into 2 equal to 20 volts in series with 2 ohm as shown. Note that the polarity of converted voltage source is such that it will drive the current in the same direction as that of the original current source. Now, observe that two voltage sources are in series across the points y1 and y2. By finding their resultant voltage source, we get plus 20 minus 5 equal to plus 15 volts with polarity as shown in series with 2 plus 2 equal to 4 ohm. Now, we shall convert two voltage sources, one of 10 volts and the other of 20 volts. By converting voltage source of 20 volts, we get 5 ampere in parallel with 4 ohm. Note the direction of the current source is upwards, which is same as the current driven by the original voltage source of 20 volts. Similarly, by converting 10 volts voltage source, we get 10 divided by 2 equal to 5 ampere in parallel with 2 ohm as shown. Note the direction of converted current source is downwards, which is the same as that of the current driven by the original voltage source of 10 volts. Now, you observe that to the right of y1 and y2, three current sources are in parallel. Hence, their equivalent will be 5 ampere plus 5 ampere minus 5 ampere, which is equal to 5 ampere flowing upwards with an equivalent resistance of 4 parallel 4 equal to 2 ohm and 2 parallel 2 equal to 1 ohm as shown. Now, by converting 15 volts voltage source, we get 15 divided by 4 equal to 3.75 ampere in parallel with 4 ohm. Note the direction of converted current source is in the same direction as that of the current driven by the original voltage source of 15 volts. Now, we get two current sources in parallel. Hence, by finding their equivalent, we get 3.75 ampere plus 5 ampere equal to 8.75 ampere in parallel with 4 parallel 1 equal to 0.8 ohm. Finally, by converting the current source, we get 8.75 ampere into 0.8 ohm equal to 7 volts in series with 0.8 ohm as shown in figure. Friends, while converting the sources, the direction of current driven by the converting and converted source has to be same. This aspect you should carefully observe. Friends, next we shall solve a question on mesh current analysis. In this question, we are required to find three mesh currents using mesh current analysis. The question is very simple and straightforward. Let I1, I2 and I3 be the mesh currents as shown in figure. By observing the network, we find that I1 is equal to 10 amperes. So, we need to write balance equations for another two loops 2 and 3. So, by writing Kirchhoff's voltage equation for loop 2, we get 3 plus 2 which is equal to 5I2 minus 3I1 minus 2I3 plus 10 is equal to 0. By substituting I1 is equal to 10 ampere and solving, we get 5I2 minus 2I3 equal to 20. Let it be equation 1. Similarly, by writing Kirchhoff's voltage equation for loop 3, we get 3 plus 2, that is 5I3 minus 2I2 minus 10 is equal to 0. By rearranging, we get minus 2I2 plus 5I3 is equal to 10. Let it be equation 2. By solving both simultaneous equations 1 and 2, we get I2 is equal to 5.7 amperes and I3 is equal to 4.28 amperes, and we know I1 is equal to 10 ampere. Friends, next we shall solve the question on nodal analysis. In this question, we are required to find current through 0.5 ohm using nodal analysis. By observing the network, we find that it has three junction nodes with two unknown node voltages V1 and V2 as shown. By writing the nodal equation for node V1, we get V1 minus 15 divided by 1 plus V1 by 1 plus V1 minus V2 divided by 0.5 equal to 0. By rearranging and solving, we get 4V1 minus 2V2 is equal to 15. Let it be equation 1. Similarly, by writing the nodal equation for node V2, we get V2 minus V1 divided by 0.5 plus V2 by 2 plus V2 minus 20 by 1 is equal to 0. By rearranging and solving, we get minus 4V1 plus 7V2 is equal to 40. Let it be equation 2. By solving the two simultaneous equations 1 and 2, we get V1 is equal to 9.25 volts and V2 is equal to 11 volts. To find current in 0.5 ohm resistance, you have two equations, one in the equation for node V1 and another in the equation for node V2. Now, using the equation for node V2, we have current in 0.5 ohm resistance equal to V2 minus V1 divided by 0.5. By substituting the values for V1 and V2, we get current in 0.5 ohm resistance equal to 3.5 amperes flowing from right to left. Is it not simple, friends? Friends, next we shall solve the question on star delta transformation. In this question, we are required to find the equivalent resistance between the terminals A and B in the network shown in figure. when we do the circuit reduction using star delta transformation, we should first identify the series and parallel connected circuit elements. If present, we have to find their equivalent and then proceed. Now, observe the given network. 10 ohm and 5 ohm are in series and their equivalent is 15 ohm as shown. Similarly, 5 ohm and 25 ohm are in series and their equivalent is 30 ohm as shown. Incorporating these reductions, the reduced circuit drawn is shown in figure. You observe that there are no series or no parallel connected circuit elements in this network. The skill of identifying the connectivity of the network elements is very important, friends. Now, observe that 10 ohm, 5 ohm and 20 ohm are in star. Similarly, 5 ohm, 15 ohm and 2 ohm are in star and 5 ohm, 20 ohm and 15 ohm are in delta. Out of these, you can choose any one network to convert. I prefer to choose delta of 5 ohm, 20 ohm and 15 ohm to convert it into star. Hope you know that for converting star into delta or delta into star, we need to remember only two equations as shown. Friends, let R1, R2 and R3 be the resistances connected in star as shown. Then R1 is equal to 20 into 5 divided by 20 plus 5 plus 15, which will give us 100 divided by 40, and hence R1 is equal to 2.5 ohm. Similarly, R2 is equal to 20 into 15 divided by 40, which will give us R2 is equal to 7.5 ohm, and R3 is equal to 15 into 5 divided by 40, which will give us R3 equal to 1.875 ohm. Incorporating these reductions, the circuit drawn is shown in figure. By observing the network, we find that 10 ohm and 2.5 ohm are in series and their equivalent is 12.5 ohm. Similarly, 7.5 ohm and 30 ohm are in series and hence their equivalent is 37.5 ohm. Similarly, 1.875 ohm and 2 ohm are connected in series and their equivalent is 3.875 ohm as shown. Incorporating these reductions, the circuit drawn is shown in figure. Observe that in this reduced network, no series or parallel network elements are present. In fact, 15 ohm, 12.5 ohm and 3.875 ohm are in delta. Similarly, 12.5 ohm, 3.875 ohm and 37.5 ohm are in star and 3.875 ohm and 37.5 ohm and 30 ohm are in delta. We can choose any one network to convert. I prefer to select 15 ohm, 12.5 ohm and 3.875 ohm delta network to transform it into star. Let R1, R2 and R3 be the circuit elements of star network. We know that R1 is equal to 15 into 12.5 ohm divided by 15 plus 12.5 plus 3.875, which will give us R1 equal to 187.5 divided by 31.375, and hence R1 we get equal to 5.976 ohm. Similarly, R2 is equal to 12.5 into 3.875 ohm divided by 31.375, which will give us R2 equal to 1.54 ohm. Also, R3 is equal to 15 into 3.875 ohm divided by 31.375, which will give us R3 equal to 1.85 ohm. Incorporating these values in place of delta, we get the circuit shown in figure. Now, you observe that 1.54 ohm and 37.5 ohm are in series and their equivalent is 39.04 ohm. Similarly, 1.85 ohm and 30 ohm are in series and their equivalent is 31.85 ohm. The reduced network is shown in figure. Now, you observe that 39.04 ohm and 31.85 ohm are in parallel and their equivalent is 17.54 ohm as shown. Finally, you find that 5.976 ohm and 17.54 ohm are in series and their equivalent is 23.516 ohm. So friends, the equivalent resistance between the terminals A and B is equal to 23.516 ohm. Friends, next we shall solve very simple and straightforward question on series resonance circuit to find the frequency at resonance. First, let us draw the circuit as shown in figure. We know that the impedance of this series RLC circuit Z is equal to R plus or minus J into bracket XL minus XC, where XL is the inductive reactance in ohms and at resonance frequency omega naught radians per second, XL is equal to omega naught L. Similarly, capacitive reactance in ohms, Xc is equal to 1 upon omega naught C. But at resonance, the imaginary part of the total impedance will be 0. Hence, XL minus Xc is equal to 0 or omega naught L is equal to 1 upon omega naught C, from which we get omega naught square is equal to 1 divided by LC and omega naught is equal to 1 divided by root LC radians per second, or F naught is equal to 1 upon 2 pi root of LC hertz. This is so simple, isn't it? Friends, finally, we shall answer the question to give comparison between series and parallel resonance. Friends, in my opinion, to answer such question, either bullet form or tabular form will be more suitable instead of essay type. So, here the answer is in tabular form. As far as the connectivity is concerned, in series circuit, coil and a capacitance are connected in series, whereas in parallel circuit, coil and a capacitance are connected in parallel across an alternating voltage of varying frequency. Frequency at resonance in series circuit is F naught is equal to 1 divided by 2 pi root LC, whereas in parallel circuit F naught is equal to 1 divided by 2 pi into square root of 1 divided by LC minus R square by L square hertz. Impedance at resonance in a series circuit is Z naught is equal to R, whereas in parallel circuit, dynamic impedance Z naught equal to L divided by RC. Current at resonance in a series circuit is maximum, whereas in parallel circuit it is minimum. Series circuit will magnify voltage, whereas parallel circuit will magnify current. Series circuit is known as acceptor circuit, whereas parallel circuit is known as rejector circuit. Finally, series circuit is used as frequency selector circuit and TV tuner circuit, whereas parallel circuit is used as a tank circuit in oscillator and also as band stop filter. Friends, After going through this tutorial, you are convinced that one should have clarity regarding the connectivity of the network elements. You should clearly discriminate between series, parallel, star and data connected network elements in the given circuit. I suggest you go through my earlier videos on open circuit concept, short circuit concept, network terminology, star delta conversion and analysis of series and parallel circuits. Hope this tutorial has kindled some of your thoughts. If so, please forward your feedback and suggestions to my email. Thank you for watching this video.